Okay, we get to go back in time and think about limits some more. In particular, we're going to be dealing with limits that have to do with infinity. Now, we already did some of this stuff back in Chapter 1. In Chapter 1, we occasionally ran into situations where a limit would equal infinity, or sometimes negative infinity. This meant, right, that as the x values approached a certain number, a in this case, the y values, or f of x values, would just get bigger and bigger and bigger and bigger without stopping. Or if the limit was negative infinity, it meant that the y values would get bigger and bigger negative numbers. Okay. When this happens, we would talk about f of x having a vertical asymptote at x equals a. For example, here's the graph of a function. You can see it sort of shoots up in the air a couple of places. It looks like at x equals -1, and again at x equals 2. Although at x equals 2 it only goes up if you come from the right. If you come from the left, it goes down a long way. So this thing has some infinite limits. The limit as x approaches -1 is infinity, because as the x values get closer and closer to -1, those y values, the graph goes up and up and up. Also, the limit as x approaches 2 from the right is infinity, because as you move from the right towards x equals 2, the graph goes up forever. On the other hand, as you move towards 2 from the left, the limit as x approaches 2 from the left, the graph goes down forever, so that limit is negative infinity. But whether the limit is infinity or negative infinity, and whether it's an overall limit or just a one-sided limit, none of that matters. If there's any limit as x approaches a number of f of x that gives you infinity or negative infinity, then you say there's a vertical asymptote. So this function has two vertical asymptotes, one at x equals -1 and one at x equals +2. So that's all stuff we did back in Chapter 1. Those are infinite limits. That's when the y values get really, really big, or really, really big and negative. What about when we want to look at when the x values get really, really big? Those are called limits at infinity. So there's technically a difference between infinite limits and limits at infinity. Infinite limits, the y values are big. Limits at infinity, the x values are big. So that means we're going to be writing the limit not as x approaches 2 or x approaches -7, but the limit as x approaches infinity of f of x. And that will just equal a number, L. So that means when the x values get really, really big, the f of x values, the y values, will approach L. X values getting bigger and bigger means we're looking to the far right of the graph. And then we will see that the y values at the far right of the graph level off at L. Okay, when this happens, we say there's a horizontal asymptote at y equals L. The other kind of limit at infinity is when x approaches negative infinity, and it's the same idea. As the x values get bigger and bigger negative, the y values will approach L. So on the graph, that means towards the left end, on the far left side of the graph, the y values sort of level off at y equals L. And again, that's called a horizontal asymptote. So here's our same function from before. We already know it's got some vertical asymptotes and some infinite limits, but it's also got some limits at infinity. As x approaches negative infinity over on the left, we see the y values sort of leveling off at y equals 2, and as x approaches positive infinity over on the right, the y values sort of level off at y equals 4. So the limit as x approaches negative infinity is 2, and the limit as x approaches positive infinity is 4. That means this graph has two horizontal two horizontal asymptotes. Y equals 2 is one of them, and y equals 4 is the other one. You can also have infinite limits at infinity. So here's a graph that as x approaches negative infinity, that means over on the left-hand end of the graph, if we go off to the left forever, as we go off to the left forever, this graph is pointing up. So its limit as x approaches negative infinity is positive infinity. its limit as x approaches positive infinity is what happens as you go farther and farther right on the graph, and in this case that goes down. So the limit as x approaches infinity is negative infinity. So this graph doesn't have any horizontal or vertical asymptotes. It's sort of diagonally asymptotic, and we're not really going to deal with that. But as you go left and right, it doesn't level off. It keeps going up or down. So there's no horizontal asymptotes. Okay, so in graphs we can find infinite limits and we can find limits at infinity, but what if you don't have a graph? Well, we use a few basic facts and a little bag of tricks. So I'll show you the basic facts in an example now, and then we'll do a lot more in class. So the basic limits at infinity have to do with the fact that when x is approaching infinity, when x is getting really big, 1 over x looks like 1 over giant numbers. 1 over a giant number is a tiny number, so this approaches 0. This limit is 0. Likewise, as x approaches negative infinity, 1 over x looks like 1 over a negative giant number. That's a negative tiny number. That's still going to 0, so that limit is also 0. These are the two sort of basic, simplest limits at infinity. But you can use the same logic for other limits at infinity. For example, 1 over x squared plus 1, as x is getting big and negative. Well, when you square a big negative number and add 1, you get a giant number, right? A giant number squared plus 1, but that doesn't really make it much bigger. That's a tiny number, so that limit is 0. Okay. If you want to take the limit at infinity or negative infinity of a rational function that is a fraction with x's on the top and bottom, the trick, the idea is divide the numerator and the denominator by the highest power of x that you see in the function. Divide both the numerator and denominator by that same power of x. That won't change the function overall. But then you can use these two basic facts that I've boxed there. So let's see what I mean. If I want to know what happens to x squared minus 1 over x squared plus 1 when x gets really, really, really big, the biggest power of x I see is x squared. So I'm going to divide that numerator by x squared and also divide the denominator by x squared. That doesn't change the fraction, right, because I multiplied by something over itself, so I'm multiplying by 1. So it doesn't change anything, but it changes how it looks. So now it looks like 1 minus 1 over x squared over 1 plus 1 over x squared. It looks more complicated, but it's easier to think about now when x is really big. Because when x gets really, really big, 1 over x squared gets really, really small, goes to 0. 1 over x squared gets really, really small, goes to 0, because x is really, really big. And when that happens, we see that what we're getting is essentially 1 minus 0 over 1 plus 0. And that's 1. So this limit, as x approaches infinity, is 1. You can do the same exact steps to show that the limit as x approaches negative infinity, in this case, is also 1. Notice that these two limits at infinity and negative infinity will not always be equal, but in this case they are equal. And this is what the graph of this function looks like. You can see that as x approaches infinity, that is to the far right, the y values are close to 1. Also to the far left, the y values are close to 1. As for what happens not on the far right and the far left, but sort of in the middle of the graph, here it's pretty easy to find the x and y intercepts. So when x equals 0, we get y equals negative 1, and so we have a y-intercept of negative 1. If I solve for y equals 0, that would be the numerator being 0, so I get x equals plus or minus 1. So there's two x-intercepts. When y equals 0, we get x equals plus or minus 1. So that lets you draw a little bit more of what the graph looks like, not at the far right and not at the far left. We'll do a lot more of this in class over the next few days. We'll see many more limits at infinity in class. I encourage you to read or at least skim the examples in the book before class, because there's a lot of things that can happen. There's a lot of different ways these problems can look, and we won't have time to do an example of every single one in class. So please read the book if you get a chance. If possible before the next class, but definitely as you're doing the homework. Here's a video question. I want you to list all the limits at infinity for this function. And tell me what all the horizontal asymptotes are. And I'll see you in class.